In section 7.6, we'll be talking about predator-prey systems. So we have looked at a variety of models for the growth of a single species that live alone in an environment. In this section, we consider more realistic models that take into account the interaction of two species in the same habitat. We will see that these models take the form of a pair of linked differential equations. We first consider the situation in which one species, called the prey, has an ample food supply, and the second species, called the predators, feeds on the prey. Examples of prey and predators include rabbits and wolves in an isolated forest, food, fish and sharks, aphids and ladybugs, and bacteria and amoebas. Our model will have two dependent variables, and both are functions of time. We're going to let R of t be the number of prey, using R for rabbits, and then we're going to use Wt, which will be the number of predators for wolves at time t. So, in the absence of predators, the ample food supply would support exponential growth of the prey. And that is, we would have dr over dt is equal to kr, where k is a positive constant. Now, in the absence of prey, we assume that the predator population would decline at a rate proportional to itself. So therefore, dw over dt is going to equal negative rw, where r is a positive constant. Now, with both species present, however, we assume that the principal cause of death among the prey is being eaten by a predator, and the birth and survival rates of the predators depend on their available food supply, namely the prey. We also assume that the two species encounter each other at a rate that is proportional to both populations, and is therefore proportional to the product R times W. The more there are of either population, the more encounters there are likely to be. So a system of two differential equations that incorporates these assumptions is as follows. We would have dr divided by dt, which is equal to k times r minus arw. And then we have dw divided by dt, which is equal to negative rw plus b times rw. And what we notice again is that w represents the predator, and that r represents the prey. And now keep in mind that k, r, a, and b are positive constants. And notice that the term negative arw decreases the natural growth rate of the prey, and the term brw increases the natural growth rate of the predators. Now, the equations in 1 are known as the predator-prey equations, or the Lotka-Volterra equations. A solution of the system of equations is a pair of functions r of t and w of t that describe the populations of prey and predator as functions of time. Because the system is coupled, r and w occur in both equations. We can't solve one equation and then the other. We have to solve them simultaneously. Unfortunately, it is usually impossible to find explicit formulas for r and w as functions of t, but we can, however, use graphical methods to analyze the equations.